we have equations like 2H2O plus 2Na yields 2NaOH plus H2. And this is actually a personal example because I once had some sodium and I threw it in the toilet. And it released some hydrogen, lit on fire, shot sodium hydroxide and sodium into my legs. And that was, so that actually happened. Yeah. But it won't be on the test, so that's just a personal fact.
You won't do it again.
I won't do it again. So here, the objects, what's the monoidal poset here? It's like chemical material collections with the arrow, that's the less than, with 0, which I don't think you would ever, that's not an oxygen, that's a 0. And plus. Oops. And by materials, I mean 2H2O, just plain old H2O, sodium, etc. So here, yeah. So one thing to note, by the way, is there's something called catalysis or catalyzing reactions in chemistry, which are things like you have some catalyst, I'll just call it K, and you have some things X and Y. And they come into a diagram, and what happens is that maybe K and X create some kind of K prime thing and X prime thing. And Y and X prime can actually interact now, and they create some kind of K double prime thing and some kind of Z thing. And the K and K double prime come together to form K again. So at the end, K comes in and K comes out, and X and Y come in and Z comes out. And so you get back your K through this kind of reaction. That can happen. I didn't write it over here, but we had this unbaked pie. And if you have an unbaked pie and an oven, you get a baked pie and an oven. And that's good. So oven is like a durable good. It kind of catalyzes the reaction from unbaked pie to baked pie. I think like literally, I guess this is a chemical reaction that this, I don't know if you could call heat catalyzing, but if so, then it does, and if not, then it doesn't. But it does whatever heat does to pies. So any questions about any of this stuff? Chemistry, the kind of chemical example. Okay, so manufacturing is almost the same. So you could manufacture a pie, right? You could manufacture chemicals. One reason to talk about manufacturing separately is just that there's an extra semantic. I'm calling it a semantic. If someone has a better word, please tell me. Extra semantic and an axiom for that semantic and an icon for our diagrams. And the semantic is waste. And what I mean by that is, in this picture here, these eggs, for example, I actually got a shell out of it too. But I didn't like that. I don't use that shell. And in the butter, when I did this, I got like a butter wrapper coming out. So this butter wrapper and stuff like have to travel through the whole diagram because they're just kept with us forever because they don't disintegrate maybe, or if they do, that would be a process. That would be another one of these boxes. But I don't want to have these things flying through, my entire diagram. I don't want to think about that. So when you're manufacturing something, or just in general, you can throw something away, and that's really useful. So I can just end this thing, or I could just end it inside. Whatever's happening in here, I could just end I could just throw it in the trash right there. And so what that axiom that's the semantic, is that you can just drop something and not have it anymore. The axiom is that for all x in P, so our thing is called P less than I tensor. Let's use the chemistry. For all x and p, x yields, you can get 0 out of it. You can have it and then have nothing. That's not true for chemistry, because if you had NaCl and H2O, you'd be rich if you could just get H2O out of it for free. Right, you can't just drop NaCl out of something. In a manufacturing process, you can, because here you have 10 to the 23 of all these things mixing around, so you can't find all your NaCls. But here, you have like a butter wrapper, so it's like not that hard to drop into the trash can. So if you can always drop anything to nothing, then you would add an extra axiom like that. And what that would look like is you have x coming in, and you can always get nothing coming out. I forgot to say that I is drawn as you just don't even have to draw your I wires. So this says x comes in, nothing comes out. But the icon I'd rather use is that picture, because it's a lot easier to just draw that. So I add this new icon, which means in my picture, at any time I want, I can take something I had and just throw the pie in the trash or whatever. Like, you can always do anything. You can always throw something in the trash. Yeah?
This example of an H2O and NaCl going to H2O, which is an example where you can't do that.
Right.
Can you explain why that's an instance of this? Because there's 0 on the right-hand side here.
Oh, right. Because if I had, yeah, thanks. So in this example, if I have NaCl going to 0, and I have H2O going to H2O, well, I definitely have this one because I'm in a, why do I have that one? Because I'm in a poset. So I have the reflexive thing for every element. And then condition A, condition A says that if I can get 0 from NaCl and H2O from H2O, then I can get NaCl plus H2O, giving just H2O plus 0. And that, by rule B, is just H2O plus 0.
I see.
Yeah.
But then in the chemical example, the thing which is violated is an A, not the absence of the...
No, A we want to keep, at least most people who do chemistry want to be able to say, if I have a reaction from A to B and a reaction from C to D, then I can take A, C and get B, D.
I see.
They want that one. They don't want to say that if they have something, it can disappear into nothing. I guess if it was some kind of I don't know, some kind of radioactive substance, maybe it would. I don't know, but that's kind of a, yeah. Other questions? Yeah, you could say you could say this one was violated. You could say this one was violated. But since these are so like useful and common, and they definitely work for the rest of chemistry, we'd rather say our new axiom is the one that was violated, since it's the combination of 3 that really give us the problem. Okay. One more example. How am I on time?
No, exactly right. Well,
Oh, nice.
we've got 1 minute for this example.
Okay. So, in information, you can also throw something away. If you have an email, you can drop it in the trash, and it's gone. But you also have, so for information or informatics, I don't know what, yeah, informatics, you add extra semantic axiom and icon. The semantic is duplicate or copy. So you cannot duplicate a physical object. That's not something you think in your manufacturing, like, oh, just duplicate that piece of chalk. But for information, you can. So if you have a calendar in front of you and you have a map program in front of you, maybe you can get an email out of it. Oh, I drafted this email. It's easy to take that email and copy it and then send it to 2 different people, to Bob or to whatever. But this is the new icon. So the new icon is, and the new axiom is, can anyone guess what the axiom would say? Yeah.
For all p, p is less than or equal to p tensor p.
Yes. For all p in my poset, p is less than or equal to, or p arrow, or whatever you want. P is less than or equal to p tensor p. P arrow p plus p. I'm going to use that. I can take p and I can replace it with pp. So that might look like p comes in, copy, 2 copies of p come out. But this is kind of big. If we're always going to add this as an axiom, we don't want to have it like, we want to have a special symbol that can reduce the clutter of our diagrams and make us only look at draft, send, and not copy. Yeah.
So this is classical information.
Yeah, classical information. Yeah. So now we have 3 different flavors of wiring diagrams we've seen. We've seen the kind of chemistry one, the manufacturing one, and this one, and they're all different flavors. And soon we'll get these even more exotic flavors with feedback and all these other things, but that'll have to wait until next time. Okay, so now we get to pure math, examples from pure math. So n union infinity less than or equal to infinity and min. So why don't you take 2 minutes and see if, first of all, this is the set, this is the relation, 5 is less than 6, which is less than infinity. Infinity is a unit, and min is the product, monoidal product. So check these 4 axioms with your neighbor to make sure that they work. Begin. They do. Oh, okay, they do. Does anyone feel like checking? Do you get it already? Is it going to work? Talk with your neighbor, see if it works. So for example, does A work? And what about does C work? Some people think it's easy, some people might not. An exercise is always good. Okay. Any thoughts or questions? Did it work? Yeah.
Why think about it this way?
Why think about what way?
Chemistry this way.
Oh, why think about chemistry this way? So what's something you know why you should think about it that way? So if there's nothing you know why you should think about it a certain way, then I can't answer the question in a context that makes sense. Like if I have sheep, I could think about them using numbers, but that might be a really stupid way to think about them. So numbers are useful, but that doesn't, right? So, so how do you want the question answered, I guess, is what I'm asking. What's the kind of thing? Yeah.
Why isn't this a stupid way of thinking of it?
Why isn't this it's self-consistent.
So what do you get thinking of this way that you wouldn't get otherwise?
About thinking about sending emails and stuff like that.
No, the chemistry one.
The chemistry one. That's something that people use in chemistry all the time, right? You have to ask them why they do it. Am I being obtuse here? Yeah.
Well, maybe, so, like, is there going to be, like, a theorem, for instance, about, these diagrams, for instance, that...
So the theorem is that, if you know that all of the pieces are true, like this is less than that, that's less than that, and that's less than that, then the whole thing is true. It's a pretty basic theorem. I guess pretty soon when we get to enrichment, you'll see how metric spaces come up, how posets come up, other things like that. But I'm not sure if that's going to satisfy you. Soon, we're also in the most basic part of this, which is all of our diagrams just move from left to right, but next time we'll have feedback where like design decisions over here affect design decisions over there, which feedback and affect design decisions over here again. So this is definitely the most simple thing, and it's quite straightforward to think about, but I'm still not sure if I'm answering your question. So you asked why is it not a stupid way? It's not a stupid, so anytime math describes something, it's not stupid to do that. Right, I think, yeah.
I guess perhaps you could say that, like, since these sorts of structures are like fairly general, that like if you wanted to know a lot about like chemistry and also wanted to know about like information theory or something else, then you could just learn one of them this way, and then you could apply it to.
Yeah, that's maybe a nice way to think of it. So another way to go off what you're saying is that you know if you made a program that understood monoidal posets, you could use that program in chemistry, you could use that program in manufacturing, and you could use that program in, what was the third one? Information, right? So something like this. You could be drawing pictures for people of recipes on how you do something with information, or recipes on how you make something. And the same program would be able to handle all those things. You would look at your rules, you would look at how you convert them into string diagrams, and you would have a software specification for the high-level way of thinking about the whole problem. Yeah.
Does this framework only work for integer number of ingredients?
No. So for example, we will do like the reals. So what do you mean?
Well, in the wiring diagram, right? Like,
Yep.
if I wanted to say that this part of my recipe used 2 eggs,
Yes.
I would have 2 egg wires.
That's right.
If I wanted to say that this part of my wiring diagram used half a cup of water,
Yeah.
then
Oh,
how do I have
yes.
a continuous net
Yeah,
quantity of
right.
input
So that's
wires?
next time.
Okay.
So next time we will be doing things where you have like water, and water is the poset, itself a poset from 0 to, all the water in the world. And then you have eggs, and eggs is a poset. And so each wire, instead of just being like 1 cup of water, will be waterness, or amounts of water, and we'll be saying, for example, velocity and the velocity and carrying capacity, or load, that a robot can handle is pitted against the cost of the robot and say, maybe that's it,
I think that's
and
probably,
power consumption. Yeah.
I think this sort of answer is the best sort of answer to this question. Monoidal posets are fairly simple structures, and there are not a lot of deep theorems about them as far as I know. But the observation here is just that this sort of basic chemical example is an example of a monoidal poset. So there are structures people deal with that fit into this framework. But we will develop the category through the category theory through this course and talk about enriching this stuff and going to monoidal categories, and then in probably the 6th lecture we'll return to a chemical-based example, and I'm not sure how far we'll get yet, but it's been shown, for example, that you can sort of define notions of open chemical reaction network as morphisms in some sort of enrichment of the structure called a symmetric monoidal category, and then this has been useful to define, say, a new notion of open entropy for reaction networks and prove that it has nice properties.
Yeah, so in other words, this stuff is kind of the stuff from, like maybe people were doing the kinds of stuff we're talking about here in the early 20th century or something, right? Where this is the very first thing we've only been talking to for like a couple hours. So in total, maybe 3.5 hours or something. So we haven't gotten to very advanced stuff, and this is not very hard to understand either. So you can't, so there's kind of a,
Anything
right.
for free.
There's nothing for free. But we will talk about places where each of the wires corresponds to a whole poset, and you're pitting velocity and load versus dollars in power consumption and trying to find like best designs and stuff like that. So feasibility relationships and other things.
When you do that, the overall structure is a monoidal poset
No.
of posets? Or is
Oh,
it-
it's called profunctors.
Okay.
It's not too much harder than what we're doing, but it's something else. Okay. Okay, so let me give a couple more examples. So So here's a monoidal poset, bool. We'll use this a lot. So this is, the set just has true and false in it. Instead of writing P, I just wrote some very small set here. False is less than true. True is my monoidal unit. And is the monoidal product. And this satisfies the conditions over here. And the last one we'll do is called Lov, or Levere. And the poset is 0 through infinity. The order is reversed. 7 is greater than 3 instead of 3 is less than 7. The monoidal unit is 0, and the monoidal product is plus. Okay, so this is an example of a monoidal poset, and the question is, what is it useful for? And now we'll get into this kind of navigation idea. So we're into the second thing, the enrichment and enrichment and navigation. So enrichment. So now we're going to use, the idea is, use monoidal posets to structure the question of getting from A to B. Okay, so what does that mean? So let me give you the definition. So let's suppose you have a monoidal poset, V less than I tensor. And V is like the classical name for when you're going to enrich in a monoidal category. So that's just what people call it. They call it V. But it's still just a regular old monoidal poset, or symmetric monoidal poset. We've talked about categories before, but now a category enriched in V or a V-cat consists of 1, a set ob X. Are called, the elements are called objects. And 2, for all, so a function X taking ob X times ob X to V. So what that says is you have a thing called objects, a set of objects, and if you have 2 objects, then you can write X of the first one and the second one, and you get a V. And we'll write down examples, so this will be less abstract soon. But satisfying 2 conditions. So soon we'll see that metric spaces are categories enriched in Lov, and that posets are categories enriched in bool. Okay. Close to metric spaces, something called Levere metric spaces. So the 2 conditions are A, that for all xy, if you have 2 objects, no, if you have 1 object, then I, which is an element of V, is less than or equal to x, the V object xx. And B, so I is less than or equal to what's called the Hom object from x to x. So we used to have something, last time I think we talked about Hom sets. Those will be categories enriched in set. But we'll get to that soon enough. So the two conditions are for all x, I is less than x of xx, and for all x, y, z, if you have three objects, then x, xy, tensor, x, y, z is less than or equal to x, x, z. Those are the two conditions. So pretty, we're going to see those conditions turn into the conditions for posets and the conditions for what are called linear metric spaces. How am I on time?
You're doing good. We've got 35 minutes left.
I have 5 minutes. What?
You've got 35 minutes left, and you've
Oh.
got 35 minutes left of material.
Okay. So posets are categories enriched in bool. So remember a poset, so this is a bit like weird because V is already a poset and now we're enriching categories in posets and getting posets back. So that's kind of strange, but we'll just say that we can recover the notion of posets as categories enriched in bool.
Just a quick question.
Yep.
Just in terms of nomenclature, so chi is both this function
Oh.
and the category itself, or
Yeah.
okay.
That's fairly common.
Okay,
Yeah.
cool.
In what sense is chi a category? Where are our morphisms?
The morphisms are, so usually we have for every x and y object, we have a set of maps x to y. Now instead of a set, we're thinking of set as like an object in the category of sets. So instead of a set, we're getting an object in the category V.
So
So-
a category enriched in set is a normal category.
Okay.
Yeah.
So what that will say is that this map from ob vx, ob chi times ob chi to, I guess maybe that should be ob v rather than v. Oh no, v is the object set.
Yeah.
Okay. So if script v was the category of sets, then v would just be a set, and that would be the Hom set.
So let's try to get, we'll go through it. And you can, I'll look at you and see if you're still questioning afterwards. So I said what a category enriched in bool is, so let's go through what a category enriched in bool is and see if we get back posets. So if chi, which I'm calling x, is a category enriched in bool, well, what are the rules? What is it? It's a set. So say x. It consists of a set of x. But let's just call this thing x. X. And two, a function that takes an ob x, it takes an x and an x and returns a Boolean, true or false. I think I wrote it better in the notes. I didn't do it in this kind of x times x. But okay, so what is that? So how we're going to convert that is if I have x of pq equals true, write p less than q. And if x of pq equals false, because it could either be false or true, right, p is not less than q. So given two things, I get a yes-no answer instead of, right? I get a yes-no answer, and that's what this function is giving me. And that yes-no answer is telling me, is p less than q or not? So here's how I'm converting the